So Federico is a senior neuromorphic researcher at IMEC, and he will talk about actually a very interesting project called spike-based neuromorphic computing for the extreme edge as a part of a joint undertaking program. So another EU-related activity that Marco and Cecile highlighted earlier. So Federico?
Thank you very much. So my name is Federico Corradi, and I'm a research scientist at IMEC. I have to say that my career has all been around neuromorphic technologies, and I would say that the most interesting part is focusing on the long-term research challenges, and for that reasons, the way in which we, let's say, our research is very much inspired by the efficiency of nature, right? And if we take the example of a bee, we can think of it as a very extreme edge computing agent. I mean, it's very efficient in power, very agile, can learn memories and associations, and can be found foraging several miles away from its nest. Of course, it does that thanks to its very tiny brain. And the idea that I always had is we have the technology to build this type of neural systems, but we really need the understanding, which is the long-term research questions. And during my career, I've always tried to look at this fundamental challenge. And for these reasons, our research is really focused on figuring out what are the differences among standard computing architectures and neural systems. And of course, there are many, many differences, and I don't want to go over them right now in details, but there are some that really interest me. For example, the standard computing architecture are based on the von Neumann architecture, in which you have fast global clocks, you have bit-perfect deterministic logic state, and you have memory that is distance to computation. You have CPU from one side and memory on the other side, and we need to keep shuffling data from one to the other. And this creates a high energy data movement, a lot of power consumption. Instead, in neural systems, those are self-timed, data-driven. There really are systems of thousands of millions of neurons, spiking neurons. They're fault-tolerant, they learn, they adapt. And most importantly, the synaptic memory is at computation. So there is some sort of co-localization of memory and computation. And so at IMEC, what we do, and what I've done also during all my career, has been building the spiking neural network devices. And here you see one of our prototypes. This is being built in 40 nanometer technology. It contains 336 spiking neurons, 200,000 synapses, and it consumes less than 100 microwatt of power. Of course, we can, the neurons in the chip are organized in layers. And the nice thing about this is that every neuron is independent from each other. There is no global clock in the chip. There is no scheduler, no state machine. Everything happens upon the arrival of a spike. And the neurons themselves, here you see a zoom of the activity of one neuron. What they do, they simply integrate input pulses. Whenever they reach a threshold, they communicate to the next neuron. And so building this technology can be actually useful in sensory signal analysis. And here you can see an example in which we are trying to classify different type of flowers, if you think of the bee, with spiking neurons. It is really important to notice that this is radically different from Neumann architecture. There are parallel nodes with memory and computation that is co-localized in the chip. Those are completely event-based. There is no clock. So when there is no data, there is no power consumption except for the leakage, of course. Huh? But this technology is also very cheap and tiny because we are exploiting standard digital technology. So nanoscale, we could go to the nanoscale level of transistor digital technology. Of course, this technology has a lot of applications, and we're only now starting to look at fields in which we can actually apply this technology. One of them is an example here in which we use one of our radar, sub-milliwatt radar sensor. It's a 8 gigahertz ultra-wideband low-power radar. We have collected a data set of gestures from this radar. We have converted them after pre-processing into spikes, and then we can do successful gesture classification just as an example of tiny machine learning that can be run on this tiny neural network, spiking neural network, neuromorphic devices. And this allows actually near and in-sensor computing. And so going to the next extreme edge level of computing, what we also started investigating is this type of technology for doing always-on monitoring of temporal feature extraction for anomaly detection. And the type of anomaly that we have been working on, we started with the use case of an insertable electrocardiogram monitoring device. This is a very tiny microchip. Again, we have implemented into it a tiny spiking neural network of 100 neurons this time and 7,000 synapses. This is more than enough to carry on the task of classifying the different phases of the ECG. But since this type of hardware needs to run on battery for a very long time, 4 years, we also need to have smart ways in which we sense and which we probe the electrocardiogram signal. And to do that, we use we innovate and we implement a novel analog to digital converter, and we call them analog to spike converter, because what they do, they really just sample the analog signal, and whenever it reaches a threshold up or down, they emit one pulse, a spike. And you see that this is really low data rate, it's enabled, and it is active on demand. Whenever the signal changes a lot, then you emit a lot of spikes. And this has been connected to our tiny spiking neural network, and we see here 4 neurons of this tiny SNN that has been trained to respond selectively to the different phases of the ECG with an accuracy of less than 1 millisecond. And this is really important if you want to do anomaly detection in heartbeat signal analysis. And so in conclusion, so our approach is really to go from applications towards neuromorphic solutions. So we really have a top-down approach in which we start, of course, by data and applications, and we try to embed those with tiny neuromorphic devices, like you see here on the right. Of course, future type of explorations could be personalizations, fitness recovery, as well as online learning, because we know that these devices, we didn't have yet implemented them with learning capabilities, but there is a lot in the community of neuromorphic. And that seems to be a very nice field to look into, especially for personalization and medical and fitness recovery. Of course, this has been done also thanks to all of my colleagues at IMEC, but also previously, as I said, my career has been built on top of EU-funded project from Horizon 2020 to now Excel undertaken. And thank you very much for your attention.
Thank you, Federico. If there are any questions, or if Mark or Cecile want to jump in. So Evgeny also, do you have a question, Evgeny?
No, just enjoy the presentation, yeah.
It was indeed a nice presentation. So I actually wanted to ask you guys, obviously this seems more appropriate for time series data versus images, for example. Can it scale okay to handle at least low resolution images?
So that's
not to the level that we saw, maybe something bigger than that.
Yeah, for sure. We are working on scaling the system up also on images. We are working on multi-core architecture of spiking neural network, let's say.
Okay.
And this is very interesting for different type of application. Like you said, if you want to go to high resolution radar system, for example, the type of imaging radar system that you would want to use in a car or in a drone, you will need a lot of more of neurons and synapses. But we start tiny, because tiny is the place to where we feel that we can really have microwatt systems, reactive microwatt systems, especially there are lots of problems that have temporal signal analysis, like biomedical signal analysis, speech recognition is another one, where we can contribute to the tinyML community. But of course, it's a very different approach than standard machine learning traditional approach.
Well, that's actually what I was going to take it from. Earlier, Daniel was discussing when we were looking at the EU presentations. Daniel mentioned about the European as being the RISC-V, essentially stereotype, if we can call it like that. Do you think that maybe we should also have spiking neuromorphic chips similar to what we just witnessed as an alternative?
Definitely, but I think also Europe is investing in neuromorphic technology, especially from a research perspective, from a technological perspective. There are lots of smart devices that I can't wait to use in my neuromorphic devices, like memory stores, all these new type of memory that can help us having nanoscale device in which we can implement neurons and synapses. I think it's definitely something that Europe is strong. There is a very large community, and part of the result that I've shown today is also thanks to the large community that we have in Europe. Also, Carlo Reta he very well knows about that.
Carlo had to step out, so he's not here to say thanks. But I think I don't know if I saw her earlier. Charlotte, I think, is with us. Charlotte gave the keynote yesterday, and she talked a lot about all this. And we had a nice tutorial on Monday by Giacomo as well. I don't know if Charlotte would like to add anything to it, since if she's here.
Actually, Charlotte and I have the same background, because actually not really the same, but we have been in the same lab with Giacomo, Professor Giacomo Individual.
Okay.
But I don't know, she's here now? Yes.
Yeah,
I'm here. Charlotte.
Yeah, I've been listening to these discussions, and I also do think that Europe has a role to play in this connection between small neuromorphic cores and open hardware. I think it's also a very important early developments, but also an important direction.
Yeah, and I think what I also can add, kind of my view from the other side of the pond. I mean, what you see here from the US, definitely there is much more activities in neuromorphic in Europe, I mean, in Zurich and France and Belgium compared to the US, and that's why I think you see more startups in the Zurich area, in France, Prophecy, and other companies. So it's really exciting to see this kind of early research that what Europe invested in neuromorphic coming kind of too many companies. I mean, it started from the academia. That's kind of my interpretation of this. Then we see, like, we saw a bunch of startups in the Zurich area, and now like big companies like Intel, Huawei, and those companies, they kind of also come and do. So basically, you develop a critical mass, you develop the ecosystem both of knowledge and talent and people, and now it kind of comes to the next phase. It's really exciting to see this from the other side from the pond. We don't have this in US because US didn't really put too much effort on this government type of funding in neuromorphic. I mean, there was some research in some academia, but it was pretty sparse and kind of rare. I think in Europe, definitely we saw like a big government investment and European community investment into this area. And now it's kind of coming again to fruition. It's great to see.
Daniel, I don't know if you wanted to add something to the discussion.
I also think like the mix is the good thing, right? You have to, if you have some workload, put the heavy stuff on these very specialized hardware, and then the stuff which is harder to put on it, you can put on some open source with Scribe or so. So Federico, can you integrate your things with kind of standard CMOS, or is this special?
Yes, so this is so what I've showed you today, it's a completely standard CMOS. And of course, the price to pay here is the error, because we are implementing everything in parallel, and everything is, but there are very good technologies, very low leakage technologies that we can use. And we hope to leverage soon the new materials coming out from the fab that actually they're investigating as well. So it's really I would say still a kind of midterm, long-term research effort to bring this technology to market. But there are interesting companies active in the field for sure.
I want to thank our sponsors that made this event possible. So the premier sponsors, Newton, working on automated tinyML. If you were there a few days ago, they had a keynote explaining what they're doing. Executive sponsors are ARM, Edge Impulse as well, and Qualcomm, Sentient. And then our platinum sponsors, we have Infineon and Reality AI. Gold sponsors are Latent AI, SensiML, and our silver sponsors are EMSA, Greenwaves, HOTG, Imagimop, GISO, Seed, and ST. And with that, I thank you very much for staying on till the very last end, the last day of the last session of the last day. And with that, I think we can close the forum for this year. Thank you everybody for contributing. Thank you, Andreas, for also moderating this session.